Having finished our discussion about memory, let's move over to our last chapter, which I call Finishing Our Design. So we have this complete router over here. Remember, this is what we're building. It has our CPU, which is the host. It has a bunch of accelerators and ASIPs over here. It has our controller for Ethernet that's moving the data real quickly. It has our interconnect that's enabling us to write this over to memory, our DMA, which is actually taking the stuff from the Ethernet, writing it to memory. We also have our, our standard slow interfaces, our UART and our GPIO. And now we've added a DDR controller plus a PHY. The PHY is, again, the thing that takes care of the physical layer. It's the really fast I/O that enables us to communicate with the DIMMs really fast. So, and the DDR controller enables us to change the order, reorder the different accesses to the to the DRAM in order to maximize our throughput and and take care of these row accesses and column accesses much better. So how do we actually do this reordering? I mean, it's really strange. If we discussed our AHB before, that was our high-speed interface that we were using. Everything was in the end ordered. We'd write data, we'd get the answer, we'd read data, we'd get the answer. So everything was really in order. That's a big problem. In AHB, we always have to wait until a transaction is finished before starting a new one. So how are we going to support this reordering that we wanted to do in the DDR? And the answer to that is also something that we talked about in the last lecture, but was kind of unclear at the time. So now I hope this clears it up. We have our next type of a protocol, which is AXI. And in AXI, we actually have different channels for each of our types of signals. So we have a write address channel, a write data channel, a write response channel, a read address channel, and a read data channel. And that means we can have different transactions going on completely simultaneously without bothering the other ones. And there's no guaranteed ordering. So we can, the CPU can send several writes and several reads, and it doesn't have to wait actually for the responses. It even can have different, sequences between the write address and when the write data is put on, because each of these different transactions is going to have an identifier. And the slave over here is going to be that DDR controller that's going to get all of these things, buffer them up and decide at which order to actually go and send them over to the DDR. And then when it gets the answer from the DDR, it's going to be able to go and send back the answer through the read address or through the write response saying it was done. So really all of these types of ACKs and NACKs, they can be done separately on each of these channels. Nothing has to be ordered, and we can get this really nice ordering over here where this is actually kind of in order, but you see that we have transactions on the address bus, we have transactions on the data bus, and these all happen before we actually get the confirmation that the data was actually written. And in the meantime, we also sent out read transactions at the same time and got the answers and so forth. And this can be mishmashed around to do at any different kind of ordering we want. And the DDR controller can therefore go and play around with this to maximize the throughput to the DDR. So that's why we have such a bus like the AXI. And it's more like a network on a chip than actually just a simple bus like the APB or AHB that we saw before. So really, we kind of completed our whole design over here, and now we understand how we talk to the DDR controller using, an AXI type of a bus rather than AHB or APB, which we saw didn't support the actual speeds we need. But one thing we saw is that this access to the DDR controller, it's problematic because we don't know how long it's going to take when we want to read something until it comes back so the CPU can use it or the processors can use it or whatever. And so what we actually want to do is we want to go and provide some of the data that we've recently accessed to be available as fast as possible. And that's why we're going to add a cache to the CPU. Well, luckily, we have a whole nother lecture that we're going to be discussing the memory hierarchy and discussing caches. So let's move on from here. Are we done? Well, I just wanted to mention kind of one more important thing. What happens on startup? And if you remember from a previous lecture, we discussed that there is something that's called startup code, where on a type of a bare metal machine, we're going to run some sort of a procedure or a bunch of instructions when we start up. But when we have a more complex system like our router over here, we're actually going to have something more complicated than that. And And it's going to start by reading what we call a BootROM. A BootROM is a small piece of memory which contains the very first code that's executed upon reset, something, I guess, like that startup code that we discussed when it was really a simple machine. And this is either going to be hardwired, often with something like a mask ROM or an embedded flash type of thing, that you can program it, again, just in case there are bugs, but it's kind of complicated to actually replace it. So it's the embedded flash is reprogrammable in some ways. Mask ROM, we'd actually have to make a new tape out for. But this is really going to be kind of hardwired. Okay, we can also use all kinds of bootstraps or fuses to change simple configurations to make differences between chips. But in general, we can consider this BootROM as something that's really hard-coded and it's not changeable. But what the BootROM does, it goes and moves on to the bootloader. The bootloader is this kind of secondary stage that we have, which is going to be usually stored on some rewritable material like an SD card, some sort of a flash card or something like that. And it's much larger. It will configure the chip and some of the peripherals. It may do things like load the end application like an operating system, which is actually going to be stored on a bigger type of storage like a real big flash disk, SSD, or even a hard drive. And then at the end, it's going to pass control to the end application, which is going to go and, in our infinite loop, going to keep on going and running whatever the router does or whatever our application is. So this is the kind of thing we have. And sometimes the BootROM and bootloader can be, combined into one on a more simple system. Sometimes there are going to be several stages of bootloaders and so forth until we get to the application. And just as another anecdote, the BootROM of an x86 system is called the BIOS. So when we turn on our computer and we configure the BIOS in something, we're really configuring the BootROM of that x86 system. So we now go back to our router and we're going to really complete the whole picture to get a whole system on chip. Okay, so we have our whole system that we discussed before with all of its parts, and now what we need is actually to add this BootROM, which is a special piece of code that's going to run, when we start up the machine. And that's not enough because it's going to probably call a bootloader, which is going to be read from some sort of memory mapped flash. So we have to have a flash controller over here that's going to connect to our SD card or our piece of flash that's going to give us our application. And now we have really our entire router on this nice little whiteboard over here. So I think that we kind of learn now how our router or how a system on chip is basically built. And I hope that closes a lot of the gaps that you guys have seen from the beginning of this lecture series until now, and we can move on to other things. Our next lectures are going to be on memory hierarchy and then on operating systems. But to conclude this lecture, which again was originally called Why CPUs Suck. So processors, they're really great at processing, but as you can see here, we may want to throw our computer away. They're not so great at data movement. They're not so great at doing all kinds of simple tasks. And in those cases, really, if it's a well-defined task, we should write an accelerator or a controller, some dedicated hardware, because it's never going to lose out to a processor. So why do we use processors? Well, one of the big reasons is because processors are flexible. We write things in software, we program them, we compile them, and we very easily get something else. Software development is much, much, much faster than hardware development, and bugs in software are much cheaper to fix. So often things change, and I just took this little joke out of XKCD, and those of you who don't know the website, it has a lot of these geek kind of comics. So if we have 14 competing standards today, well, 14, that's a ridiculous number of standards, and we really need to develop one universal standard that covers everyone's use cases. Yeah, let's go and do it. And now we have 15 competing standards, and then we have to go and reprogram the thing. So we better have a processor, something that's programmable and rewritable over there to be able to support it. So just to finalize this lecture, I think it's a really cool lecture. I really loved it when Tsachi originally made it. So the original lecture that Tsachi gave in 2019 was called Interfaces, External or Internal, or Why CPUs Suck, when I asked him to give this kind of lecture. And I adopted it and kind of added a little bit of stuff, but really it's only about, it's about 80% based on what Tsachi described over there. And I took a bunch of stuff from the great book that's called Computers as Components by Wolf. So that's all for now, and next time we'll be discussing the memory hierarchy.